So in continuation to the previous lecture, where we discussed about the detection techniques, and in particular we discussed about envelope detector, which is a kind of a pretty simple demodulation technique for basically the conventional AM type of signal, because that already has a carrier signal in it, right? So envelope detection was a asynchronous type of detection, since it does not require it does not require the carrier signal at the receiver end. So a locally generated carrier is not required at the receiver, hence simplifying the circuit to a greater extent. Second type of detection technique is synchronous detection. Synchronous detection, as the name suggests, it is the type of detection in which we require a locally generated carrier signal at the receiver, and that has to be perfectly synchronized in both frequency and phase. So I'll just first draw the block diagram of it, and then we'll discuss the step-by-step functioning. So we have a multiplier as the first block, which multiplies your AM signal with the carrier, locally generated carrier signal CT, that is your AC cos omega CT, and the output of this multiplier is passed through a low pass filter. The cutoff frequency of this low pass filter is set equivalent to the maximum frequency component present in the signal, and the resultant is your message signal. The expected resultant is your message signal. Okay, so for the perfect reconstruction of the message signal, it is assumed that this carrier signal, which is locally generated through a local oscillator, this carrier signal should be perfectly synchronized in both frequency and phase. It should be perfectly synchronized in phase and frequency to that of the carrier signal used at the transmitting end. That means this carrier signal should be exactly similar to the carrier signal that was used to modulate the signal, basically, right? That is the concept. So now you can clearly see here the circuitry required to perform the synchronous type of detection is quite complicated as compared to the circuitry required for the envelope detection, right? In here we need a multiplier, we need a local oscillator to generate the carrier signal, which is quite a complicated task. This generation of carrier signal at the receiver is requires a whole lot of circuitry in itself. So this is quite a complex circuit as compared to the envelope detector, right? So if you look at the mathematics of it, and if you try to study the step-by-step process of synchronous detection, let us assume the case. We'll have a look at the analysis by assuming the case 1, that there is a perfect synchronization of the carrier signal, perfect synchronization. This carrier signal is it's assumed to be perfectly synchronized with the carrier at the receiver end. Alright. So the first step is multiplication. Let us assume we take conventional amplitude modulated or DSBC type of a signal. We know the standard expression of that, and that consists of your carrier signal plus multiplication of your message and the carrier, AC MT cos omega CT. The first step is the multiplication of the modulated signal with the carrier signal, right? That is, we multiply this SAMT by the carrier signal. That is the first step. So this will result into AC cos omega ct plus AC mt into cos omega ct into AC cos omega ct, right? And now if we simplify this expression further, we get AC square cos square omega ct plus AC square mt cos square omega ct, right? This is what we get. Now let us apply some trigonometric identities and simplify it. We get this becomes AC square by 2 1 plus cos 2 omega ct, and this will become AC square mt by 2 into 1 plus cos 2 omega ct. Alright. Now if we further pass this signal through a low pass filter whose cutoff frequency is omega m, that is the maximum frequency component present in the message signal. Now if you look at this signal, there are different components. This AC square by 2 is a constant entity, does not affect the signal, that can be suppressed at any point of time using some discrete elements. Then second element is AC square by 2 into cos 2 omega ct. The frequency component present is twice of omega c, which is much larger than omega m, hence this will get eliminated. Next component is AC square mt by 2 into 1, right? So the frequency component present in here is omega m, the frequency of mt signal, right? That will be passed through this low pass filter. So one of the component that will pass is AC square by 2 into mt, right? Next component is this multiplied by cos 2 omega ct. So the resultant frequency component will be plus minus of the frequency component, that is 2 omega c plus minus omega m, and that is certainly much higher than omega m, hence that will also get eliminated. So we are left with only this component after we pass it through a low pass filter, and that is AC square by 2 into mt. Now the required signal we know is your mt. What we are getting is a scaled version of mt, right? And I've already told you that we need not worry about the scaling factor because that can be eliminated at any point in time. That is not a big concern. So we can see that the resultant we are getting is some scaled version of our message signal, which is the desired thing for us, right? So this is how synchronous detection takes place, assuming perfect synchronization, right? This is a synchronous detection assuming perfect synchronization. That means this locally generated carrier is perfectly synchronized with the carrier used at the transmitting end, which was used to modulate the signal, right? So it's a basically two-step process and very simple. Broadly looking, it's very simple, but this generation of local carrier and the multiplication process itself is a quite a complicated task. All right. So it's a two-step process. First is multiplication of your AM signal with the carrier signal, and then further passing it through a low-pass filter. Now let us have a look at the case 2 of the analysis, that is, which is a more practical case. That is, there's no perfect synchronization available with us, and there is some phase, you can say, distortion in the locally generated carrier signal. So we assume that the carrier signal, the locally generated carrier signal through the oscillator is your AC cos omega ct plus phi. So phi is the phase difference in the carrier signal which is generated at the receiver end. Okay, so now if we perform the same analysis, the first step is multiplier. So we multiply the AM signal with the carrier signal, that is cos omega ct plus phi, rather AC cos omega ct. Alright, so now if we substitute the value, this AM signal, that is your AC cos omega ct plus AC mt into cos omega ct multiplied by AC cos of omega ct plus phi. And if you simplify it and further pass it through low pass filter, I am skipping the intermediate steps and moving on directly to the low pass filter output. The resultant signal would be your AC square by 2 MT into cos of phi, right? Where AC square by 2 is clearly a scaling factor that can be eliminated. MT is our message signal, that is the desired signal. Cos phi is the distortion introduced in the demodulated signal. Okay, and this distortion will vary in accordance to this angle phi, right? So if this phi is 90 degree, depending on the value of phi, this distortion will vary. If the phi is 90 degree, if this phi is 90 degree, we know that cos 90 degree is your 0, and hence that will result into total loss of the signal, right? Isn't it? If phi is 90 degree, the cos phi is 0, that means the detected symbol will be equivalent to 0. That is total loss of the signal. This condition is known as quadrature null effect. Quadrature null effect. When there is total loss of the signal due to the phase error as 90 degree. Hence we call it as quadrature null effect. Quadrature is that introduces a orthogonal phase error, and null effect means it totally distorts the signal. Okay, so depending on this phase error, cos phi is the phase error introduced, there will be some distortion in the detected symbol. Now moving on to the third type of the detection technique, that is the square law detectors. Square law detector is basically you can say a variant of the synchronous type of detector only. So in case of square law detector, I'll first draw the block diagram and then we'll have a look at the working of it. We use a square law device. Input is your amplitude modulated signal, and we further pass it through a low pass filter whose cutoff frequency is again the frequency maximum frequency component present in the message signal MT. So the working of it is pretty simple. The function of the square law device is to, if this is, let's say, V2 signal, so the relationship between V2 and the input is V2 is equal to A1 into the input plus A2 into the square of the input. This is the relationship, or you can say the function that is being performed by this square law device. Alright, its square law device is nothing but you can say a circuitry made up of discrete elements that perform this kind of a operation and maintains this kind of a input-output relationship. So this V2 will be equal to A1 into, here you can substitute the expression of the amplitude modulated signal and here the square of that, right? And if we further simplify it and further pass it through the low pass filter, low pass filter will eliminate all the higher frequencies and will try to keep the lower frequencies only. So the low pass filter output will come out to be A2 square by AC square by 2 into MT, which is nothing but again the scaled version of your message signal, which is the expected value. So this is the third type of the detector, that is square law detector. But the most commonly used type of detectors are your either synchronous detection or your envelope detection that we did in the previous lecture. And obviously this synchronous and the synchronous detection is kind of a coherent type of a detection in which the carrier signal is required, a locally generated carrier signal is required at the receiver end, while in the case of envelope detector, no such requirement of generation of locally generated carrier is required, and it's a very simple circuit. Okay, so till now we have seen three type of amplitude modulations. Your DSB-C, which is conventional amplitude modulation, then DSB-SC, double sideband suppressed carrier, and then SSB-SC, single sideband suppressed carrier. Now moving on, we'll have a look at the fourth type of the modulation scheme, that is vestigial sideband modulation. Vestigial sideband modulation. We'll have a look at the, you can say, the logic behind this vestigial sideband modulation and need of this. So far, SSB-SC was one of the best modulation technique in terms of the transmission efficiency and the power efficiency. Transmission efficiency and power efficiency was best in case of SSB-SC modulation. But the drawback associated with SSB-SC type of modulation scheme was that the demodulation process is complex. Demodulation is complex. Reason being, if you look at the frequency spectrum of SSB-SC, it either consists of upper sideband or lower sideband. It has only a single sideband, right? And it is usually formed using your DSB-SC kind of a signal, right? Isn't it? So if this was a DSB-SC type of a signal, so it is usually formed using a frequency discriminator circuit or the phase discriminator circuit, and it is really difficult to design such an ideal filter, low pass filter or a high pass filter, right? Or for this matter, passband filter. Because the filtering action is usually, if you look at the practical filtering action, it is something like this. The frequency response is something like this. It is not exact orthogonal, right? So we can say that it becomes really difficult for the demodulation as well as for the generation part of the SSB-SC, although it has significant merits associated with it. So the application of this SSB signal was limited to voice signal only. It was limited to voice signal only because the spectrum of voice signal is such that there is a guard band between the two side bands. Okay, so the spectrum of the voice signal is something like this. This is FC. There is a sufficient guard band between the two side bands. Hence, it is really easy to distinguish and to separate out the two side bands using the filtering process, even the practical filtering process. It is really convenient to filter out this kind of a signal. Hence, this vestigial sideband of modulation technique is preferably used for the voice signal only. Alright. Not the vestigial sideband. This SSB-SC type of the signal is preferred only for the voice type of signals. Now, in order to deal with this situation of ideal filtering, we come up with another type of a variant of, you can say, SSB-SC, that is vestigial sideband modulation. Let us have a look at the vestigial sideband modulation first, right? This vestigial sideband modulation technique, it almost provides the same bandwidth. The bandwidth requirement is almost same as the bandwidth requirement of SSB-SC. Hence, we can say it is equally bandwidth efficient scheme, and it also allows video signal transmission, which was not allowed in case of the SSB-SC signal, because the video signal transmission frequency range is 4.5 megahertz. The frequency component present in is 4.5 megahertz, and there is no guard band between the two sidebands, right? Now, what is the principle behind vestigial sideband modulation? In case of vestigial sideband modulation, what we do is, in SSB-SC we pass only a single sideband, either lower sideband or the upper sideband. In case of vestigial sideband modulation, what we do is we pass a vestige. So let us say that this was the suppressed sideband. This dotted one is the suppressed sideband, and this is the passed or the desired sideband, and this dotted one is the suppressed sideband in case of SSB-SC modulation. In case of vestigial sideband modulation, what we do, a vestige part of this undesired sideband is also taken into consideration, and an equal amount of the desired sideband is eliminated. So this kind of a signal is being transmitted in case of vestigial sideband modulation. An equal and opposite, some part of this, or you can say a vestige part of the undesired sideband, which is this, is passed, and the similar area, similar part of the desired sideband is eliminated. So if you look at it, the overall there's no loss of information. The exactly same part is being added and eliminated, right? So this is your the spectrum of vestigial sideband modulation scheme. It helps us to use the practical filtering process. It helps us to use practical filtering process. That is the advantage of using vestigial sideband, and you can clearly see it's just a variant of SSB-SC type of modulation and helps us to use the practical filtering process. I'm repeating once again, a vestige part of undesired sideband is included in the signal, and a similar part of the desired signal is eliminated. So in totality, there is no loss of the information. That is the concept of vestigial sideband modulation scheme. The process of generation of vestigial sideband modulated signal is again pretty simple. First we generate a DSB-SC type of a signal. We use a multiplier that can be a balanced modulator or ring modulator that multiplies the message signal and the carrier signal. So the resultant signal, we know it is DSB-SC type of a signal with two sidebands, right? Then we further pass it through vestigial sideband filter, VSB filter, and the expected output is supposed to be VSB type of a filter. So if we carefully analyze the bandwidth requirements of all the modulation techniques discussed so far, you'll find that the bandwidth of your DSB-C or conventional and DSB-SC is twice of omega m, which is the largest. Then after that we have vestigial sideband, and then SSB-SC. The least bandwidth requirement is of SSB-SC, but there's a very slight difference between the bandwidth requirement of these two, vestigial sideband and SSB-SC. In case of SSB-SC, the bandwidth requirement is omega m, because we are passing only a single sideband, right? So this is nothing but omega m. But in case of VSB, you will see that the bandwidth requirement is something omega m. If this range is, let's say, omega v, so bandwidth is omega m plus omega v, where omega v is a very small quantity, so bandwidth is almost comparable for these two. But if we compare it quantitatively, the bandwidth of SSB-SC is least amongst all the modulation schemes. Okay, and in terms of power requirement, obviously the power of DSB-C and DSB-SC is largest, and power of DSB-C is largest because that has carrier component as well as two sidebands. Then we have DSB-SC, we suppress the carrier signal, and then we have VSB and SSB SE. So power requirement for VSB and SSE is same, and it is least. Alright, so clearly we can see that in terms of power efficiency, VSB is performing quite well. In terms of bandwidth efficiency also, it is quite comparable. Okay, and it overcomes the issues of SSB SE as well. So we can say that this VSB SE is a kind of a very efficient technique.